Hello everyone, welcome to Adson Engineering Academy. It is me, your tutor Adson. As I told you in the previous video that we shall be solving a combination of different loads. Today we're going to solve another problem, that is problem number 3, a combination of a uniformly varying load and a UDL. So please stay tuned, watch our previous video and get to understand how to solve this one too. Let's dive into today's problem, which says draw the shear force diagram and a bending moment diagram for the beam provided below. So as I told you in the previous video that we shall be having a combination of different loads. So today I'm telling you that we're going to solve a problem with a combination of uniformly varying load and then uniformly distributed load. Now if this is a reaction force at A and this is a reaction force at B, the first thing I have to do is to find this reaction forces. So reaction at A plus reaction at B will be equivalent to the downward forces, which the first one is a uniformly varying load, and to change it into the force I told you in the first video, so please watch that video how to convert a uniformly varying load to a concentrated load. So get the area of this triangle, half times 3 times 4. You've converted it already into what? Into concentrated load, and then plus 8 times 3. You have converted this UDL into what? A concentrated load. So reaction at A plus reaction at B, this will be equivalent to, this is 6 plus what? 24. You get 30. Now let's take moment at this point A. So when you take moment at point A, I am going to have first of all this uniformly varying load, if I convert, is what? Is 6. Okay, if you convert this uniformly varying load into a concentrated load, you get 6. So 6, which is a force due to this triangular loading, I'll multiply with the distance. Let's say the centroid is here. So the centroid being here means this part is 2/3 of the span, which is 3, then this part is 1/3 of the span, which is 3, from here to here. Okay, so that means I want the distance from this part to this part, which is what? 2/3 of what? 2/3 of the span, which is what? 3. Well, plus let's go to the next force, which is UDL. UDL is 8 kilonewton per meter, but the total what? The total span given is 3. If in 1 meter it is the 8 kilonewton, what about in 3 meter? So that means it's 8 times 3. So this is going to be equivalent to reaction at B times the, what is the perpendicular distance from B up to A, so that is 8. So you realize that when you solve this value of RB is coming to a clean answer of 21 kilonewton. Then if you substitute this RB in this equation, this one, you get RA, and the value of RA is coming to be 9 kilonewton. Well, we have solved for the reaction at this one, reaction forces. Now let us go and find the shear forces. At each span, we're going to start with a span of 0 to 3 meter. A span of 0 to 3 meter, first of all we have reaction at A, which is 9. So that means that will be what? Shear force X is equals to what? 9. And then minus the shear force, which is due to what? Due to this triangular loading. So if I cut this from here, so from here to this point, if I call it X, so meaning that I will have to get a small triangle. So let me just put it here, a small triangle, because I'm cutting at a distance X. So I need to find this value. What is the value if I compare to this big triangle? Okay, so you realize that this W, if I call this part W, comparing it, just similarity, okay, comparing it to this, so W out of 4 will be the same as X out of what? X out of 3, which is for the bigger triangle. Now if I make W the subject, this is 4x out of 3. So that means this small triangle is 4x out of 3. If I continue now to solve, that means that I will have to what? To find the area of a small triangle, which is half times the distance is x, and then times what? Times this small triangle. Okay, half times the distance is x, then times this height is what? 4x out of 3. So here I have 4x out of 3. So this area of this small triangle is just a force due to that small triangle. So what is the shear force when the value of x is equals to 0? If I substitute x to be 0, the shear force here is what? Is 9, and this is in kilonewton. Then let's have the value of shear force when the value of x is equals to 3, because we're working within span 0 to 3 meters. So if I substitute, this is going to be 9 minus this is half times 4 by 3, then times x is x squared, but the value of x is 3, so 3 squared is 9. Okay, so if you simplify this, definitely you will come to an answer which is 3 kilonewton, because this and this will cancel. So this gives us what? 2 here, and this will cancel. This gives us 3 here. 9 minus 6 is 3 kilonewton. So the shear force there is 3 what? Kilonewton. Well, let's move to the second span, which is from 3 meter to 5 meters. At this point, from this part to this part, remember I am taking the origin here, so the span is increasing up until the last span, which is what? 8. Okay, so we are now at this point, which is 3 meter to 5 meters. At this span, since there is no load, that shear force will remain constant. Okay, so it will remain what? 3 kilonewton. No need to even waste time doing it. It is just 9, which is the for the what? Reaction force, then minus the force due to what? Force due to triangular loading, which is 6. If you what? Change it. So which is 6. There is no load in between. It remains constant. So this still remains 3 kilonewton. And let's have the last span for shear force, which is 5 meter to 8 meter. Well, in this case, here what do we have? We have a UDL, and this is the UDL that we have. So for you to get this shear force, let's get shear force x. The expression is going to be, we have 9, which is at the first one, then minus the one due to triangular loading. Okay, the one due to the one due to triangular loading is going downwards, so it's going to be what? Minus 6. Okay, minus 6. And then we have the force that will come due to UDL. Okay, so let's say that means we are cutting this beam from here, and the span from here up to where we have the UDL is what we're calling x. But if that is the case, that means we are only considering the portion of the UDL which is what? From here up to this point, of which I need to know this span, this part is what I need to know. So that means this is going to be minus 8 times the distance, because I need to know the distance to change it into force. Okay, so the distance here, if from here up to here is x, then from here up to here should be the total, which is x, then minus from here up to here, which is 5. I will remain with only this distance. Hope that is clear. So this will be x minus 5. So when I substitute my shear force at when x is equals to 5, this answer is 3 minus 8 into 0. Okay, 5 minus 5. So this answer still remains what? 3 kilonewton. And then let's have the next part. When shear force when x is equals to 8. So when I substitute here, this is 3 minus 8 into what? Into 8 minus 5 is 3. 8 into 3 is 24. So 3 minus 24 is negative 21 in kilonewton. We are done with getting all the values for the shear forces, and with all the information we have calculated, we can sketch it. So I will sketch at the end. Allow me to take you through how to calculate the bending moment. Well, so remember, this is our figure, and if we need to calculate the bending moment, we are going also span by span. Let's start with span 0 to 3 meters. So mx, which is the moment that I want, the expression, I start with the first span 0 to 3. So I cut the beam from here. Okay, so that means from here up to this part I'm taking it as x, and that small triangle is what I have drawn here, as you can see. So the span from here up to here, from the origin up to x, then this value at this point is 4x by 3. You need to understand this part clearly, otherwise you cannot do it, but it is easy. Now if that is the case, that means I will have to consider the first thing is 9 times what? The span, the distance, which is x, so 9x. 9x, then minus what is the moment which is coming from the triangular loading. Since I'm taking only from here up to here, which is x, so I have to first convert this small what? Small triangle with span x into a force. And to do that, you get the area. So the area is half times x and then times 4x by 3. This is the what? The area of a small triangle. This small triangle that I had drawn. Okay? Now, if I've found the area, that is equivalent to the force. But I need the moment. Okay? I need the moment when I'm standing at this point, x. Okay? X from A and A. Now, if that is what I want, that means I have to know that I have to multiply with the centroidal perpendicular distance from the what? From where this force is acting. This force, if this to this part is x, this force, let's say it is acting at the centroid here, and from this it is 1/3 to this part and it is 2/3 to this part. Hope you have got that point clearly. It is 1/3 to this part and it is 2/3 to this part of x. So that means since I'm taking from here, then it will be 1/3 of x. So the distance this force due to x, span x on the triangle is causing is times 1/3 of x. So now what will be my expression? You can simplify it. This is 9x minus, you can reduce this, as you can see this is 2, so this becomes 2 out of 9. Okay, 2 out of 9, then x times x times x is x cubed. Now let us get the value. What is the value of moment when my x is equals to 0? Definitely this is giving you what? 0 kilonewton meter. Okay, then let us also check when my x is equals to 3. What is the value of what? What's the value of the moment? So this is 9 times 3, then that is 27. Okay, then minus this is 2 by 9 times, what do you have here? This is 3 cube, and what is 3 cube? 3 cube is 27. So 27 definitely will reduce this to what? To this is 9, so it will reduce this to 3 only. Okay, so that means 3 squared will go away from here. So 2 times 3 is 6. So 27 minus 6, the answer here is 21 kilonewton meter. Well, so I believe that is the right calculation that we needed for that span. Let's do for the second span, which is 3 meter to 5 meter. Yes, so for 3 meter to 5 meter, just the same way how we have been doing it, let's also have in place mx. Okay, let me have the diagram again. This is what we have, and I am within 3 meter to 5 meter, so this is going to be 9 times x, because I'm cutting the beam from this, I'm cutting the beam from this middle part. So that means because I'm working from 3 meter to 5 meter, so if I cut the beam from here, that means from this part to this part will be x. So 9 times x, that is for the first case. Then the second force that is falling there is triangular loading, and this triangular loading, if I convert it, it is coming to 6. You know, it is coming to 6, the force due to that triangular loading, because area is half times 3 times 4, so this is 6. But where is it acting? It's acting at 1/3 of 3 from here. So that means 1/3 of 3 is 1. So from here to this part where it is acting, it is only 1 meter. Then from here to NA, it is 2 meter. So that means if it is acting, leaving 2 meter behind, so that means the distance from this to this part is what I need. From this part where it will be acting to this part, okay? I mean from the centroid of this bigger triangle, okay? So it is leaving 2 meter behind. Well, So that is going to be total, which is x, because of the total span from here up to here where I've cut the beam. But from where it is acting, it is leaving 2 meter behind because I want only this. So let me subtract away what? This 2 meter. Okay? Yes. I believe if you've got that point, it is quite easy. Now let us substitute. When my x is equals to 3, what do you get as this answer? This is 9 times 3. Obviously that is 27. Okay? Then minus x is 3. 3 minus 2 is 1. 1 times 6 is 6. This answer is still coming to 21 kilonewton meter. This is good. Now let us what? Let us do for when, what is the moment when my x is what? 5. Okay? So when my x is 5, in this case, I'm going to substitute 9 times 5. So 9 times 5 is 45 minus 6 times 5 minus what? 5 minus 2 is 3. 3 times 6. So that means this is 3 times 6, 18. So what is the value of 45 minus 18? So this answer is giving us a clean value, which is 27. This is 27 kilonewton meter. Now we are left with finding the last one. Okay? Yeah. So let's work with the span 5 meter to 8 meters. Okay? So mx due to that is going to be equals to 9 times x, because we are cutting the beam from the UDL. Okay? Since we are cutting the beam from here, so 9 times the span is x. Then what about the force, the moment due to the uniformly varying load? So this is going to be minus 6 into x minus 2 as done in the previous one. So check on that so that you don't miss it. Then minus the force that is coming due to what? Due to the uniformly distributed load, this one. So that means, first of all, what do we have? We only have this because we have cut it from here. So that means this is the only UDL part that we are considering. Okay? Yes. So that means I have 8 times the total distance there is x, but I only need this distance where UDL is covering. So that means I have to take away what? From here up to A. So this is 2, this is 3. So that is 5. Okay? So this is x minus 5. By doing this, 8 is the value of the uniformly distributed load times the distance which is covering, which is x minus 5. Okay? So that is only the force. We have just converted into the force. If I need to make it as the moment, I have to multiply by half of the distance, because this is the distance which is at x minus 5. But if I multiply, where is it acting? It is acting what? At half of what? X minus 5. So that means I have to multiply with the distance where it is acting, which is x minus 5, but at half of it. Okay? I believe you have got this point. Please take note of that so that you can what? Not miss what? Interpret it. So let's find the value of moment when my x is equals to 5. Okay? So when my x is equals to 5, you got to substitute. This is going to be 45 minus, this is 6 times this is 3. Okay? Then minus, obviously if this is 5, you clearly see that this is going to be 0. 5 minus 5, 0. So the answer here still remains what? Like the previous one, which we obtained to be 27 kilonewton meter. Okay? Well, what about the value of moment when my x is equals to 8? The value of moment when x is equals to 8 is going to be 9 times 8, then minus 6 into, this is 8 minus 2, this is 6. Okay? Yes. And then minus, this is 8 into, this is out of 2 into, this is x, which is 8 minus what? Minus 5. But since the two of them, I can just put a square here. So totally this answer is coming to 0 kilonewton meter. Okay? So you check on that carefully. Now, one thing that I would love to, when we're drawing a bending moment, a point is reached where the UDL, in where we have the UDL, this part, when we're drawing it, it's where it's going to be maximum. So we need to obtain it within this point. So for that case, we need the value of x where it is going to cut this line. Okay, so we have to go back to our previous work where we were finding the shear force. Okay, well, so this is our shear force within that span. We found the expression was 9 minus 6 minus 8 into x minus 5. So I wanted to show you that, so that we first we equate this shear force to 0. So 9 minus 6 is 3, then minus 8 into x minus 5. So let us equate this to be 0. We want to find where shear force is 0. What is the value of x where shear force is 0? Okay, so at that point I will have to take this the other side. So 3 equals to 8 into x minus 5. So this is 3 by 8 equals to x minus 5. So the value of x here, okay, is coming to 5.375. But from where? That is from NA. Okay, so that means from here up to where, when we're drawing the shear force here, where it will cut this line at 0, it's what? 5.375. Well, so if this is the case, that means there should be the value of the moment. Remember, where shear force is 0, that is where moment is maximum. So let us find the value of what? The moment when the value of x is 5.375. So this is going to be 9. Okay, it's the same thing. 9 times 5.375, then minus, this is 6 into 5.375 minus 2. Okay, then minus 8 by 2 into 5.375 minus 5 and square this and this. Okay, yeah, so this answer is coming to 27 point, if you press it very well, okay, you have to verify that using your calculator, 0.563. So this is our maximum bending moment. Now allow me show you how these values we have obtained can be drawn. I have drawn it ready here clearly, but I will explain how it has been obtained. As you can see, now this is the shear force. We found that in our first case that the value of the shear force at this point was 9. Okay, it's 9 kilonewton, so we have drawn it to 9. And since this is uniformly varying load, it is going to produce x squared, which is a parabolic. So you have to draw a parabolic curve. At this point we found the value was 3 kilonewton. Please check the calculation, 3 kilonewton. Okay, so that means here you have to write here 3 kilonewton, and it is what? Parabolic up to this point. Because there is no force in between this, it remain constant. 3 kilonewton remain constant up to here. Okay, and I've told you that there is calculation where this force is what? Crossing here, cutting this one at 0. Okay, so from this NA up to this point, it is where what we calculated. But from here is 3, here is 2. That means here is what? The other remaining, because this is 5. Then the other 0.375 is this one. So that means this part is 0.375, where it is crossing what? The value of x at that point. Now it came down because this is UDL, so it is drawn with slanting what? Line like this. But what is the value of the figure here? This is 21 kilonewton. And good enough, here was 21 kilonewton upward, so it counterbalanced it to bring it back to 0. So this is how to draw the shear force diagram. This is FSFD. Now let us draw, I'll show you how the bending moment has been obtained. At this point, this is 0. We found that it was 0. Okay, and we came to this point. This value we obtained it from the calculation. We found it was 21 kilonewton meter. 21 kilonewton meter. Now which curve is this? Since it was x cube, this curve is cubic curve. Okay, so you need to understand how it has been drawn like that. Why not like this? It's a cubic curve. Wow. So from this span 3 to 5 meter, this span, there's no load there, so this point to this point, it is just drawn straight like this, just joining like this, not horizontal. Okay, yeah, so it is joined from here to this point because it is moment. Okay, so from this point to this point, and this point is 27. Okay, so 27 kilonewton meter. Now from 27 kilonewton meter, at the point where it has crossed, what shear force has crossed this, it's where we have the maximum bending moment, and this value we obtain it to be 27.563. Okay, from the calculation, the maximum bending moment that we obtain. Okay, then lastly, this thing curves back to 0. So I believe this is a clear explanation of how to draw the shear force diagram and bending moment diagram. In our previous video, we had a correction to be made. As you can see, this is SFD. In the previous video, this was connected straight to this point, but correctly it is supposed to be from this point to this point, remaining constant, then a sudden change under the point load up to 12.5, then remains constant till the end. So please watch the previous video and correct that SFD. Thank you so much for watching that video till the end. We have fully understood how to draw the shear force diagram and a bending moment diagram. So please, if the video is helpful to you, do like the video, comment, share with your friends, and above all, subscribe to this channel so that you don't miss any of my video.